From the dawn of humanity, the stars have captivated us. They twinkle in the night sky, distant suns scattered across the vast expanse of the universe. These celestial objects are more than just points of light. They are cosmic furnaces, powered by a phenomenon known as thermonuclear fusion. This process, occurring deep within the core of stars, is the engine that drives the universe as we know it. Our very existence is intertwined with the fusion reactions happening trillions of miles away. The warmth we feel from the sun, the light that illuminates our world, the energy that sustains life, all stem from the fusion of atoms in the sun's core. Fusion is the process that has fueled stars for billions of years, and understanding it is key to unlocking the secrets of the cosmos. The sun, our nearest star, is a giant ball of plasma, a state of matter so hot that atoms are stripped of their electrons. In the sun's core, the temperature reaches a staggering 15 million degrees Celsius and the pressure is immense. Under these extreme conditions, hydrogen atoms, the simplest and most abundant element in the universe, are forced to overcome their natural repulsion and fuse together. This fusion process releases an incredible amount of energy, radiating outwards from the sun's core and into space. This energy is what we experience as light and heat. Fusion is not a chemical reaction like burning wood or exploding dynamite. These familiar reactions involve the rearrangement of electrons around atoms, releasing energy in the process. It is a nuclear reaction, a process that involves the nuclei of atoms, the very heart of matter. Unlike chemical reactions, nuclear reactions tap into the core of the atom where protons and neutrons reside. In a chemical reaction, atoms share or exchange electrons, but their nuclei remain unchanged. This is why chemical reactions, while powerful, are limited in the amount of energy they can release. In a nuclear reaction like fusion, the nuclei themselves are altered, leading to a profound release of energy. This alteration involves the merging of atomic nuclei, which fundamentally changes the nature of the atoms involved. Fusion occurs when two or more atomic nuclei, the positively charged centers of atoms, combine to form a heavier nucleus. This process releases a tremendous amount of energy, which is the key to the power of stars. This process might seem counterintuitive. After all, like charges repel each other. The positively charged protons in the nuclei naturally repel each other due to electrostatic forces. However, under the extreme temperatures and pressures found in stars, atomic nuclei are moving at incredibly high speeds. These conditions are so intense that they allow the nuclei to collide with enough force to overcome their natural repulsion. These speeds are so high that the nuclei can overcome their electrostatic repulsion and get close enough for the strong nuclear force to take over. This force is much stronger than the electrostatic repulsion, but only acts at very short distances. The strong force is one of the four fundamental forces in nature and is responsible for holding the nucleus of an atom together. It binds protons and neutrons tightly within the nucleus, making it incredibly stable. The amount of energy released during fusion is enormous, far greater than any chemical reaction. This is because the energy comes from the binding energy of the nucleus, which is much more substantial than the energy involved in electron interactions. This energy is released according to Einstein's famous equation, E equals mc squared, which states that energy, E, is equal to mass, m, times the speed of light, c squared. This equation shows the direct relationship between mass and energy. In fusion reactions, a tiny amount of mass is converted into a tremendous amount of energy. This conversion is what powers the stars, providing them with the energy to shine brightly for billions of years. This is why stars like our sun can shine for billions of years, powered by the fusion reactions in their cores. These reactions are a testament to the incredible power locked within the atomic nucleus, a power that fuels the cosmos. The most common type of fusion that occurs in stars is the fusion of hydrogen nuclei or protons to form helium. This process is fundamental to the life cycle of stars and is the primary source of their immense energy output. This process, known as the proton-proton chain reaction, is a multi-step dance of atomic nuclei, culminating in the creation of a helium nucleus and the release of energy. Each step in this chain reaction is crucial and involves complex interactions between subatomic particles. The first step in this intricate dance involves two protons colliding at incredibly high speeds. These collisions are driven by the extreme temperatures and pressures found in the cores of stars, which are necessary to overcome the repulsive forces between the positively charged protons. One of the protons undergoes a transformation, changing into a neutron and releasing a positron, the antimatter counterpart of an electron, and a neutrino, a nearly massless, chargeless particle in the process. This transformation is a rare event, but it is essential for the continuation of the fusion process. This newly formed neutron is now bound to the remaining proton, creating a deuterium nucleus, also known as heavy hydrogen. Deuterium is a stable isotope of hydrogen and plays a key role in the subsequent steps of the fusion process. In the next step, another proton collides with the deuterium nucleus, fusing with it to form a helium-3 nucleus, which consists of 2 protons and 1 neutron. This step releases a significant amount of energy, contributing to the overall energy output of the star. This fusion process releases a gamma ray, a high-energy photon, carrying away some of the energy released during the fusion reaction. Gamma rays are a form of electromagnetic radiation and are one of the primary ways that energy is transported out of the star's core. Finally, 2 helium-3 nuclei collide, fusing to form a stable helium-4 nucleus, 2 protons and 2 neutrons, and releasing 2 protons back into the stellar cauldron to participate in further fusion reactions. This step is crucial as it ensures the continuation of the proton-proton chain reaction. This final step completes the proton-proton chain, converting 4 protons into 1 helium nucleus, releasing energy in the form of gamma rays, positrons, and neutrinos. The energy released in these reactions is what powers the star and allows it to shine brightly. This fusion process is the dominant energy source for stars like our Sun, which are classified as main sequence stars. Main sequence stars are characterized by their stable fusion of hydrogen into helium, which defines the majority of their life cycle. The energy released from the fusion of hydrogen to helium in the Sun's core creates outward pressure that counteracts the inward pull of gravity, keeping the star in a state of equilibrium. This balance is delicate and essential for the star's stability. This delicate balance between fusion and gravity is what allows stars to shine steadily for billions of years. The continuous fusion reactions provide a constant source of energy, enabling stars to maintain their luminosity and support life on surrounding planets. The fusion of atomic nuclei is not a trivial task. It is a process that requires immense energy and specific conditions to occur. It requires overcoming the electrostatic repulsion between the positively charged nuclei, which necessitates extraordinary conditions. This repulsion is a fundamental force that keeps atomic nuclei apart under normal circumstances. The heart of a star provides the perfect environment for fusion to occur: extreme temperatures and pressures. These conditions are found in the core of stars, where the environment is hostile and intense. Temperature plays a crucial role in fusion by giving atomic nuclei the kinetic energy they need to overcome their electrostatic repulsion. The higher the temperature, the faster the atomic nuclei move. At extremely high temperatures, atoms move at incredibly high speeds. This high-speed movement is essential for the fusion process. These high speeds mean that when atomic nuclei collide, they do so with enough energy to overcome the electrostatic force and get close enough for the strong nuclear force to bind them together. The strong nuclear force is what ultimately holds the fused nuclei together. Pressure also plays a critical role in fusion by increasing the density of the stellar core. The higher the pressure, the more densely packed the atomic nuclei are. The higher the density, the more frequent the collisions between atomic nuclei. This increased frequency of collisions is crucial for sustaining the fusion process. In the core of a star, the immense gravitational pressure squeezes the atoms together, increasing the likelihood of collisions and, in turn, the rate of fusion reactions. This gravitational pressure is a key factor in maintaining the conditions necessary for fusion. The Sun's core, for example, has a temperature of about 15 million degrees Celsius and a pressure over 200 billion times that of Earth's atmosphere at sea level. These extreme conditions are what make the Sun an efficient fusion reactor. These extreme conditions are necessary to overcome the electrostatic repulsion between protons and allow them to fuse. Without such conditions, fusion would not be possible. The energy released from these fusion reactions then counteracts the immense gravitational pressure, preventing the sun from collapsing under its own weight. This balance between energy release and gravitational pressure is what keeps the sun stable. The relationship between temperature, pressure, and fusion rate is crucial for understanding the life cycle of stars. These factors determine how a star evolves over time. As stars age, they consume the hydrogen fuel in their cores, leading to a decrease in the rate of fusion reactions. This decrease in fusion rate marks a significant change in the star's life cycle. This decrease in energy output causes the star's core to contract, increasing the temperature and pressure. The contraction of the core is a natural response to the reduced energy production. This increased temperature and pressure can then ignite the fusion of heavier elements, such as helium, allowing the star to continue shining, albeit at a different stage in its evolution. The fusion of heavier elements is a key phase in the later stages of a star's life. Understanding the intricate balance of temperature and pressure in stellar cores helps us comprehend the various stages of a star's life, from its birth in a nebula to its eventual death, whether as a white dwarf, neutron star, or black hole. Each stage is governed by the principles of nuclear fusion and the delicate interplay of forces within the star. In the case of massive stars, the fusion of heavier elements can lead to a dramatic supernova explosion, scattering elements across the cosmos and seeding the universe with the building blocks of new stars and planets. This cosmic cycle of birth, death, and rebirth is a testament to the power of nuclear fusion and the fundamental forces that drive the universe.